Guys, I'm very happy to have Jenn here today. It's been a while. We were first in touch speaking about she might come to talk here, and actually since that time, every time I asked, we had a lot of speakers since then, and every time I asked, like, do you know any awesome speaker, who is around here, who we should invite? There was, let me think. You should definitely invite Jenn Wortman. She's doing some really cool work at UCLA. So I'm really happy that we have her here today. She got her bachelor from Boston University, her master's from Stanford. She spent some time at Harvard before she did her PhD at the University of Pennsylvania with Michael Cairns. And now she's at UCLA, where she's actually the recipient of a career award from NSF. And she's also the Symantec chair for the firm. So Jenn has been working on algorithmic aspects of economics, on machine learning, as well as social computing. She has co-founded Women in Machine Learning annual workshop, and she's very active in many machine learning conferences. In fact, she was just giving a tutorial at ICML in Edinburgh, in Scotland, and she was also the area chair there and organized the workshop there. So I'm very much looking forward to her talk on prediction, beliefs, and marketing. Please welcome Jenn Wortman.
Great, thank you. Can you guys hear me? I've been told that there are some issues with this microphone, so.
It's awesome.
Great. So I feel a little bit guilty giving this talk at a machine learning meetup because this is not a machine learning talk per se. But I'm going to be talking about a lot of things that are kind of related to machine learning. In particular, I'll be talking about markets that are used for aggregation in much of the same way that learning algorithms are used for aggregation. And I'll also be talking a little bit towards the end about some very formal and beautiful mathematical connections that exist between markets and machine learning algorithms. So there will be some connections in there somewhere, even though this is not, really a pure machine learning talk. In this talk, instead, I'm going to be focusing on the design of prediction markets. So let me start by just talking a little bit about what a prediction market is. So a prediction market at a very high level is basically just a financial market, but the main difference is that the goal of running a prediction market is to aggregate information and get predictions out of the market. So an example that is often used is the website Intrade.com. This is a prediction market website that is run out of Dublin. It's illegal to run markets for real money in the US, so it's run in Dublin. They have all sorts of securities, and the key property is that the payouts of these securities are linked with some future event. So for example, you can go to Intrade and you can find securities like this one. This security will pay off $10 if you hold this security if Obama is re-elected president, and it will be worth $0 otherwise. So this is either worth $10 or nothing. If you think about it, if you're a risk-neutral and rational trader in this market, so basically if you want to maximize your expected payoff, and you think that the probability of Obama being reelected is P, then you should want to buy this security at any price less than $10 times P, right? Because with probability P, it will pay off $10. And similarly, you should want to sell the security at any price that's greater than $10 times P for the same reason. And so for this reason, you can kind of think about the current price of this security as measuring the population's collective belief about how likely it is that this particular event is going to occur. And you can see here that this security, this was as of last week, I think the price hasn't changed that much. This security was trading at $5.60 a share, and since this is a $10 security, that maps to an estimate of there being a 56% chance that Obama is going to win the election. So that's the idea behind a prediction market. I'm going to give a couple more examples. I've already mentioned Intrade. They have political securities like the one that I showed on the last slide, but they also have securities for other types of events. So things like entertainment events, the security will pay off if The Dark Knight Rises breaks the all-time opening weekend box office record. And they have some stranger ones too, like the security here that will be worth $10 if NASA announces the discovery of extraterrestrial life before the end of the year. This is actually trading at 43 cents right now, so they're saying there's a 4.3% chance that this will happen, which is maybe a little bit high. If you think about it, the people who are buying this security are really not paying that much for it, so maybe they're willing to take a big risk here. Maybe they're not actually risk neutral. I don't know. But kind of interesting to see people's predictions.
Because there has to be somebody on the other side?
Yes. So I'll talk about that a little bit later. But yeah, there are people trading on both sides here. Another example that people talk about a lot is the Iowa Electronie Market. This is a market that actually somehow managed to get permission from the government to run for real money in the US. It's university run. They do mostly political markets. This is just showing the prices for securities for a Democrat to win and a Republican to win the 2008 presidential election, going from around the middle of 2006 up until the election. So you can see that, over time, this sort of measured people's opinion of how likely it was that the Democrat or Republican was going to win. And it looks pretty reasonable. There are some strange things like this spike here on the Democrat security, but overall it's about what you would expect. Another example that I like is Inkling Markets. Inkling is a company that actually designs prediction markets for other companies to use internally. So you could go to Inkling and they would put together a market for you for something like, will this product that we're launching complete testing on time? And then you can internally have everybody in your company come in and bet on this and try to get information from people who actually know whether this product is going to complete testing on time and try to get a good prediction that way. These internal prediction markets have actually been used by a variety of companies. They've been used by Google and HP and Microsoft and other companies to try to get predictions like this from employees who may be afraid to go up and tell the management that they really don't think that this product is going to finish on time, but maybe they're willing to bet on it, something like this. So I've been talking about prediction markets as a way of gathering these predictions. So the question that you might have is, how good are these predictions? So there is some theoretical work here talking about aggregation and how good these predictions should actually be. This theoretical work says that under a certain set of assumptions about the traders and their information and so on, the prices in a market like this should converge to an equilibrium that has the property that the prices reflect everybody's collective beliefs all together. So basically the prices that you arrive at should be the same as the probabilities that you would come up with if you knew all of the private information of everybody who is interacting in these markets. That's great, but the assumptions that you have to make in order to get these results are really, really strong. They're kind of standard economic assumptions, but they're things like you need all of your traders to be Bayesian and doing Bayesian updating based on what everybody else is doing. You need all of your traders to have a common prior over the event. You need all the traders to know each other's information structure and things like this. So probably not very realistic for real-world traders. What might be a little bit more convincing is that in practice there have been countless studies published showing that the predictions from these markets actually are pretty good. So this dates back to things like in the 80s there are studies where people were looking at orange juice future prices, and they are actually more accurate at predicting the weather in Florida than Florida weathermen on TV. Right? And there have been studies showing that election markets are more accurate than polls, and so on. There have been a ton of these. You have to kind of take this with a grain of salt because, of course, if you have a study in which your prediction market totally fails and the predictions are terrible, it's a lot harder to get that published than a study where your predictions are actually really good. So, it's not clear how many other cases there have been where the predictions weren't so great, but there at least seems to be a lot of empirical evidence to show that these predictions that you get out are pretty good. So when I gave this example of the security at Intrade before, I said that the current price as of a week or so ago was $5.60 a share. I want to talk a little bit about how we actually determine this current price and what this should be. So there are a couple of different ways that you could come up with this price. What's done on Intrade is to use something like traditional stock market style pricing. So basically they use what's called a continuous double auction. This is what's in the stock market. They have these order books, buy orders and sell orders, and they match up people on both sides to make trades with each other. So this works really well for the stock market. This works pretty well for securities like this one here for Obama being reelected because there are a lot of people who want to trade this security. This does not work so well for securities like the NASA discovering extraterrestrial life security that I showed earlier because there just aren't a lot of people who want to trade this security. Right? So if you look at that security on Intrade, at least as of a week or two ago, I think people were trying to buy for around 10 cents and sell for around $2.50, something like this. So there's a pretty big spread there. So that doesn't work so well if you have kind of a small pool of traders. What I'm going to talk about in this talk instead is pricing these securities using an automated market maker. And the idea here is that we're going to have this market maker who's essentially an algorithm who's running this market. And this market maker is going to be willing to take some amount of risk in order to encourage trading. It's kind of key that the person running this market, the person running this automated market maker has to be willing to take some risk because taking some risk will actually encourage traders to come into this market and trade with each other even if there aren't a lot of traders. Okay. And this automated market maker is essentially going to be an algorithm that's always willing to both buy and sell securities. So we'll see how that can work. Okay. So before I get into the new stuff here, let me talk a little bit about what's been done so far in terms of the design of these automated market makers for pricing securities. So a lot of the literature so far has focused on what's called complete markets. In a complete market, we assume there's some set of mutually exclusive and exhaustive events. So we have some set of events, and exactly one of those is going to occur. And we're going to have one security associated with each of these different events. So, for example, we might say that there are two events. There's the event that Obama wins the election. There's the event that Romney wins the election. Of course, in the real world, there is some small possibility that neither of these events is going to occur, but we'll kind of ignore that and assume for now that we know that exactly one of these two events is going to occur. Okay. So in a complete market, then we would have one security associated with each of these two events, and just to make things simple, we're going to have each of these securities pay off $1 if the event happens and be worthless otherwise. And again, an automated market maker for this setting would always be willing to buy and sell each of these two securities at some price. So the typical type of market makers that people have looked at in practice tend to be run using the idea of a cost function. Okay, so let me just explain how this would work for this particular example. So let's think about this market that we're running. The market's going to have some current state, which we can summarize by the number of shares of each security that have been purchased so far. Right? So we're going to say that, in this case, Q1 shares of this first security have been purchased, and Q2 shares of this second security have been purchased. Okay? And we want this market, with this current state, to be able to price new orders that come in. So imagine that we have a new trader coming into this market now, and he would like to buy R1 shares of the first security and R2 shares of the second. Here, these can be 0, they can be negative, representing a short sell, or they could be positive. Right? Typically, you would expect maybe one of these would be positive and one would be 0. So the algorithm that we have, this automated market maker, needs to be able to somehow price this purchase given this current state of the market. Okay. With the cost function-based market, this purchase will be priced using a cost function, C, which is essentially a potential function. So basically, we define this function C in advance. This is going to determine the behavior of the market-making algorithm. Okay. And the way that this purchase would be priced is that the total cost of this purchase to the trader would be this cost function C evaluated at kind of the new state of the market, so evaluated at this Q vector plus this R vector, which is our new state of the market, minus this cost function evaluated at the old state of the market. Right, so you can kind of think about this as a potential function that's measuring how much money the market maker has collected so far. And basically, if we set up the market this way, then all we need to do in order to specify the entire behavior of the market maker is to specify this C function, this potential function. So you might wonder at this point, where these prices went in this market, right? We said that we want to be able to get these prices out of the market, and we're going to be treating these as our predictions or probabilities. And it's kind of easy to see, if you think about it for a minute, that if we're using this cost function type of market, then we can get these prices out by taking the derivative of this cost function with respect to the number of shares that have been purchased. Essentially, these prices here, these derivatives can be thought of as the price per share of purchasing an infinitesimally small number of shares of either of these securities. So these are going to be our prices, and these are going to be our predictions also. Since these are worth $1, then these are going to correspond to our probabilities, our predictions of how likely it is that these events occurred. Are there questions about this setup so far? I didn't say this at the beginning, but anyone should feel free to interrupt me with questions at any time.
Why are you using both Q1 and Q2? So it sounds like, so say I've bought 10 for Romney and 5 for Barack Obama, but 5 and 5 will cancel out, so that'll be equivalent to cash. So you practically need only one of them.
Yeah, so in this case, if we just have these two different outcomes, you could get away with just having one of these, and since we're using a cost function like this, it will all cancel out. Basically, whether to have just one of these securities or to have both is more of a user interface question than anything else. But you could get away with just having one. In general, if we have k different outcomes, we could have k-1 securities that we're offering. But in that case, it seems a little bit nicer to include all of them rather than just including k-1. But you're right that for this particular example, it probably wouldn't be that bad to just include one of these. Other questions so far? Okay. Good, so this is how a cost function-based market works. Let me give you an example of the type of cost function that we might expect to see here. So one that has been used a huge amount in the literature is what's called the logarithmic market scoring rule. This cost function has a form that is probably familiar to many people in this audience if you have a machine learning background, because functions like this pop up in machine learning all the time. We'll talk about these connections a little bit later. But essentially, the logarithmic scoring rule cost function has this exponential form. Here, B is just some positive parameter that affects how quickly the prices change. And the instantaneous prices here are, again, just the derivatives of this cost function. Again, these Q's are the number of shares of each security that have been purchased so far. It's not important to understand the exact form of this, but let me just point out a couple of properties of this that are useful for us in designing a market. So the first property I want to point out is that if we look at PI, the instantaneous price for security I, this is going to be increasing in QI, the number of shares of that security that we've purchased so far. And in fact, it's increasing exponentially fast in this quantity. And this makes sense if you think about it, right? Because we want these prices to be reflecting the public's opinion. And we really need it to be the case that if people are, say, purchasing the Obama security, we want the price of that security to go up. It would be strange if it went down when people were purchasing the security. The other thing that I want to point out about these prices is that they sum to 1. And if we sum over all of the different outcomes here. And that also makes sense when we're thinking about complete markets for a couple of reasons. So the first reason is that, as I said before, we want to be interpreting these prices as probabilities of all of our different events. And if they're going to be probabilities, we need them to sum up to 1. The second reason is that we actually need this if we want to prevent arbitrage from occurring in this market. Right? So if you think about it, in this complete market setting, we have one security associated with each of these mutually exclusive and exhaustive events. And so if these prices summed up to something less than 1, then a trader could come into this market and buy one of each security and be guaranteed that he would get $1 in return, right? Because we know that exactly one of these is going to pay off. And similarly, if we allow short selling, a trader could come in and sell one of each of these securities and be guaranteed to make a profit as well. So for both of these reasons, it's kind of important here that these prices should sum up to 1. Good. This has some other nice properties as well, but I won't get into those now. Yes?
Small person. What is J is I know what I is. J.
Oh, so this is summing over all of the different events. So in this case, this would sum over the Obama security and the Romney security in the example. But in general, we could have more than those 2 events. Okay. Yeah.
Sorry, what's B again?
Oh, so B here is just it's some positive parameter you can set however you want that impacts how prices change and impacts some other properties of the market as well. Okay.
So let me see. I'm trying to think like if Q is this QI? Is it the history of all purchases?
Yeah. So that's
So
the total number.
It would seem like people bought a lot of Obama, say, early on, and now people are starting to buy Romney. That you shouldn't necessarily use. I mean, the past is kind of a sunk cost, isn't it?
That's a good question. So you could imagine some market that looks at the fact that people in recent history have been buying a lot of Romney securities. Maybe we should make that price go up faster and kind of ignore what's been happening in the past. That is not done in these cost function based markets in general. Typically, it's kind of left up to the traders to pick up on this kind of thing. So you would assume that, if traders are noticing that a lot of Romney securities are selling and they think that this is happening for a reason, then they should keep buying until the price reflects their current belief. Right? So, some people have looked at trying to have markets that are a little smarter, try to learn something from recent behavior of traders, that type of thing. But here, we're kind of putting all of that burden of aggregation onto the traders themselves and just not worrying about that in the market maker at all.
So people can sell back the
Yes.
securities, right? So holding a security is a decision in the present, even if you bought it in the past. So the fact that these people are still holding the security says something about their current opinion of the underlying thing.
Yeah, exactly. And here we typically allow short selling when talking about these markets too. So even if you haven't bought it in the past, you could short sell if you think that the security is way overvalued. So basically leave it up to the traders to set the prices. Okay. We can come back to that issue later maybe, but let's move on for now. So this logarithmic market scoring rule that I've mentioned has received a lot of attention in recent years. But being computer scientists, I've been talking to a lot of people about running this type of market over much larger outcome spaces than something like this 2-outcome election scenario. So you could think about trying to run a market for, say, the election, but instead of having an outcome be just Romney wins or Obama wins, you could try to get something much more fine-grained. So you can try to do something where we define an outcome now to be a vector of size 50 that tells us who the winner is in every single state, something like this. And this type of market is something that people are actually interested in running. There was a group of people who were, until recently at Yahoo Research in New York, who were trying to implement a market very much like this. And there's still a group working at this small company called PredictWise that is trying to run a market very much like this, where an outcome might be an entire vector of who's going to win in every state. And there are a number of reasons that you might want to do this. It allows people to, first of all, tell you much more fine-grained information that they might have. Right? There's not a lot of expressive power if we just have these 2 different outcomes. We can get a lot more information from people if we have more complex outcomes. But it also makes the problem a lot trickier. In particular, if we have an outcome space like this, we can't just run this logarithmic market scoring rule that I mentioned on the previous slide, because it's actually been shown that calculating prices in that market is intractable if we have a really, really large outcome space like this. It's also kind of intractable for humans if you want to think about humans betting on some particular outcome if we define outcomes as these large vectors. Right, so if you're a human, maybe you can give me a reasonable estimate of how likely you think it is that Obama is going to win, but you probably can't give me a very good estimate of how likely you think some particular outcome over all 50 states is going to be in the election. People are notoriously bad at these small probabilities. So we were thinking about how we can run these markets over these very large outcome spaces without making things intractable. What's typically done in practice is that people just run a bunch of separate independent markets and don't link them up. Right? So if you think about something like a horse race where an outcome is really an entire permutation of horses in the race, typically if you go to a horse race, you can bet on things like the horse that's going to win, or the horse that's going to place, which means come in first or second place, and so on. And these markets are run mostly independently of each other. And this is a little bit strange. We're kind of throwing away some information in this case, because certainly if a huge number of people are betting on a particular horse to win, then the price of that horse placing should also go up. These things are dependent. So the goal of the work that I'm going to be talking about for most of the rest of this talk is to actually be able to design sensible market makers for these potentially very large outcome spaces, given some set of securities that we want to price, which is maybe, I said small here, it doesn't necessarily have to be small, but small relative to the size of one of these 2 to the 50 size outcome spaces. I mean, we want to be able to do this in a way such that the prices that we get out are consistent, we don't have all of these independent markets, and we wanted to do it in a way that this can all be operated efficiently. Okay. So this is the problem that I'm going to be talking about, and then I'll talk a little bit more about the connections to machine learning. Are there questions up to this point? Pretty good? So good. So this is our problem. Before I move on, let me think about, or talk a little bit about how we can formally define this problem, how we can actually state what it is that we want to do here. Okay. So we want it to be the case that we can price some set of securities over this really large outcome space. So the first thing that we need to do is give the person who's going to be running this market some way to specify the particular securities that they want to price. So in order to do that, we want it to be as general as possible. So we did this using kind of a general payoff function. And if you want to think about this payoff function, I think the bottom of my screen is cut off here, but there's nothing important down there. You can think about this payoff function kind of in your head as a matrix where we have one row for every outcome. So these are all of the different states of the world. And one column for every security. And the entries of this matrix are going to tell us how much the security in this column is worth if we're in this state of the world, or if this is the true outcome. Okay. So just to give an example to make this a little bit more concrete, if we think about something like this case where our outcome space is a permutation, so something like this horse race setting, then we could think about having one row for every possible permutation outcome, and maybe we want to do something like allow bets of the form, this security is going to pay off $1 if and only if horse I finishes ahead of horse J. Right? And then would have one column for each IJ pair, where the security for C coming out ahead of B would be worth $1 for all of those permutations where C comes out ahead of B. Right, so this is the type of thing that we have in mind. Since we're talking about really, really large outcome spaces, we don't necessarily have to be able to write down this matrix. It might be really, really huge, but this is just kind of a good way to visualize what's going on with this payoff function. So once the person running this market has specified this payoff function, they've specified what securities they want to have in their market, we want to be able to design some type of market maker to price these securities. So, there are lots of different ways that you could do this. There are lots of different market makers that you can come up with. I mean, a market maker is essentially just an algorithm that tells us what these prices are going to be. But we somehow want these prices that come out to be reasonable. We don't want them to just be totally arbitrary. So the next question that you have to think about here is, what does it mean for these prices to be reasonable? So I talked about this a little bit already in the complete markets case, where we have one security for each outcome. Right? In that case, I said that one property of being reasonable is that all of our prices should sum up to 1. Right? And again, this was so that we get out a probability distribution, and also so that we prevent arbitrage. If you think about something like this pair betting setting that I just mentioned, where we have permutation outcomes and we want to allow bets of the form horse I finishes ahead of horse J, it's less obvious what reasonable means. Okay? So you could think about this for a while and come up with various conditions that you want. Right? So maybe the first condition that you would come up with is, well, if we have a security for horse I coming out ahead of J and a security for horse J coming out ahead of I, we want the prices of these to sum up to 1. Because, again, we know that exactly one of these is going to pay off $1. Is that enough? Well, you could think about this for a while longer and come up with other conditions that you might want satisfied. So, maybe you want it to be the case that if we have 3 horses and we have a security for I coming out ahead of J, J coming out ahead of K, and K coming out ahead of I, we want the prices of these to sum up to something between 1 and 2. And this is, again, for similar reasons. We know that at least one of these 3 is going to pay off $1, and no more than 2 of these is going to pay off $1. But is this enough? Well, it's not really clear. If you think about it more, it's not clear if this is enough or if there's something else that you want. And in general, if we just allow some arbitrary large outcome space and some arbitrary set of securities, it's even less clear kind of what makes prices reasonable. So to attack this question of what makes prices reasonable, we tried to be a little bit more specific about what we mean by reasonable here, what properties we want our market to satisfy. So we did this using an axiomatic approach and came up with a set of axioms which you may or may not agree are desirable properties that we want, but we kind of need to start somewhere to say what reasonable is. So let me talk a little bit about the axioms that we define that we want our market prices to satisfy for aggregation. So the first axiom that we defined, it may not be the first thing that you would think about, but I'm putting this first because it actually simplifies the problem a lot if we require this axiom, is what I'm calling path independence. And this says that if we have a trader who's coming into this market and he wants to purchase some bundle of securities R, and here again, R is a vector that says how many of each security this trader wants to purchase, then the trader should pay the same no matter how he kind of breaks up this purchase. So the idea is slightly more formally is that if the trader is coming into this market and he wants to buy some set of securities R plus R prime, so this is a vector saying how many of each he wants, and we've got some fixed history of trades that have happened in the past, then the amount that he pays for this should be the same as if he purchased first this bundle R and then immediately purchased this bundle R prime. So you can debate whether this is desirable or not. We think that this is desirable because it takes an incentive issue out of play. So now, again, we want these markets to be aggregating opinions, so we want traders to really be giving us this information that they have, and we don't want them to be worrying about the optimal way to break up different purchases they might want to make. We want them to just figure out how to put their information into the market and do it. This property is also really nice because it actually allows us to restrict ourselves to thinking just about this cost function formulation that I mentioned earlier. So it turns out that this path independence property is actually equivalent to stating that we can design our entire market maker just using one of these cost functions or one of these potential functions that I mentioned earlier. So this is kind of convenient. It just tells us that we don't need to think about all possible algorithms for pricing in the entire world. We can just limit ourselves to thinking about these nice cost potential function based algorithms, like the logarithmic market scoring. I'll go through the other properties that we wanted a little bit more quickly. So first of all, we wanted it to be the case that instantaneous prices actually exist, right? And this is because, again, our goal is to use these markets to get out predictions, and so we need to be able to get predictions out all the time, no matter what, right? And this property is basically equivalent to requiring that this cost function C that we have is differentiable, because again, as I mentioned before, these prices are just going to be the derivatives of this cost function. We wanted it to be the case that our market actually incorporates information in the proper way. So this is getting at this idea I mentioned earlier, where if people are buying the Obama security, we want the price of the security to go up. Right? So in general, we want it to be the case that if a trader comes in and purchases some set of securities, it should never cause the price of that set of securities to decrease. We want to prevent arbitrage. I mentioned this earlier in the complete market case as well. By this I mean that we never want it to be possible that a trader can come in and purchase some bundle that gives him a guaranteed profit in the end, no matter what the outcome is. This is desirable from the perspective of the person who's running the market because, if we're allowing these arbitrage opportunities, we're essentially just throwing away money that the market maker could be keeping. So we don't want to be doing that. We'd rather have it be the case that we restrict arbitrage, we don't have this happen, and the market maker gets to keep this extra money.
Jen, can you dig into the middle one just for a second?
Yeah.
I mean, the idea that if someone's buying something, like in the stock market, if people are buying things, that means people are selling things. And if the sellers are accepting lower and lower prices, you can have huge volume days where prices go way down, right? So what's the impact on the reality of the prediction you're making that you're saying that can't happen? Or are you really saying that can't happen? I mean, it sounds like you're saying that as long as someone's buying it, that person's value has to go up.
Right, so when I'm talking about these automated market maker-based markets, we're assuming that all trades happen with the market maker, so with this algorithm who's running the market. So if somebody is purchasing this security in this case, they're purchasing it from this centralized market maker, who's just this algorithm we're running. Right? There's nobody on the other side who's selling it to them. Right? If somebody then came in and wanted to sell that same security, this property would require that the price would immediately go back down. So,
Okay, so basically an infinite number of one thing can be purchased without anything being sold. So that's why you make separate this.
Yeah.
Okay.
Exactly. Yeah. So in this type of market, we don't have any limit on how many contracts there are existing. You can kind of you can buy countless contracts from this market maker, and that will just keep the price going up. Although, I mean, eventually it will level out, but yeah, but it will never cause the price to drop. That's a good question. Yeah. And the last property that we want is what I call expressiveness, and this says that traders should always be able to set the market prices to reflect their beliefs. What this really means technically is that if we have a trader who has an infinite amount of money at his disposal, and this trader was able to buy infinitely small fractions of securities, then it should be the case that the trader can always get the market prices to reflect his beliefs. But again, we want this because we're using this market to make predictions, so we want people to actually be able to put all of their beliefs and all of their information about these securities into the market. Yeah.
Given the cost function that y'all have set up, and it takes into account this proposed purchase that's about to happen when setting the price, right? So that would prevent somebody from buying and then immediately turning around and selling right after the price went up because of their purchase.
Exactly.
Right?
So if somebody does that in a cost function based market, they'll break even every time. Yeah. Because essentially, because of the way that this cost function works, the instantaneous price is changing as you buy. So, you know, if you buy 2 contracts, then the instantaneous price for the price you're paying for the first is going to be less than the price you pay for the second. Exactly. Okay. Good. So these are the properties we want in the market. And it turns out that by stating this set of properties, we can actually very precisely state the entire set of markets that satisfy the properties that we want. So let me put this result up, and then I'll explain what this actually means in words. So this result says that under these 5 conditions or axioms, if we want a market maker that satisfies these, then the costs that this market maker sets have to be determined by some cost function C. This cost function C has to be convex, and this cost function C has to satisfy this kind of strange looking property here. So what this property says, if we look at it, is that, well, on the left-hand side here, we have, you know, the set of all possible gradients of this cost function. And as I talked about before, you know, these gradients are essentially the price vectors for all of the different securities. So this set on the left here is a set of all different possible price vectors that we could get to using this market. And what I mean by this hull of the price function on the right here is, well, if we go back to this matrix representation of our price function, we think about having one outcome in each row and one security in each column. What I mean here is the hull of the rows of this matrix. So all possible convex combinations of the rows of this matrix. So this is telling us that we need our cost function to satisfy this kind of strange property that the set of reachable price vectors is exactly the set of convex combinations of these rows. If we think about kind of a simple example to try to get a sense of what this actually means, if we think about the complete market case, right, where we have one security associated with each outcome, and we look at what the hull of the securities is in that case, well, the hull of these rows is just the probability simplex. So in this complete market case, this gives us exactly what we want, which is that our prices have to sum up to 1. But this kind of tells us a way to generalize this idea to more complex markets. Yeah?
Is that an if and only if statement?
Yes, it's if and only if. The statement is slightly imprecise. The precise statement has some ugly boundary conditions that you need to worry about, but it is an if and only if. Yeah, so this completely characterizes all markets that have these properties that we want. Okay. So, that's nice. We have this mathematical characterization, but this particular property here is a little bit strange, right? We're saying that we want to be able to find some function c that satisfies this weird property about its set of gradients. So the question that naturally comes to mind is, how do we actually find a cost function that satisfies this property that we want? And I'm going to do a huge amount of hand-waving here, but it turns out that we can actually borrow some nice tricks from convex analysis that give us a very clean and nice way of doing exactly that. So I'm putting up this fact here. This is one of those things that either you are very familiar with convex analysis, you've seen this a million times, it's obvious to you, or you're not familiar with convex analysis, this looks totally mysterious and you have no idea why something like this would be true. I was in the second group when we started working on this project. I'm not going to try to convince you that this is true now, but this is just kind of a useful fact for us here. So this says that if we have some closed differentiable function c, it's convex if and only if it can be written in this particular form here as a soup of a dot product minus this function r that's called the conjugate of c. So just take my word on this for now. There's also this other nice fact from convex analysis that says that if we want to know the gradient of a convex function, the gradient is just this vector x that maximizes this expression here. So I'm going to again wave my hands a lot here, but this fact is really useful for us because we want to be talking about convex functions, and defining them based on their gradient. And this fact allows us to essentially do exactly that. In particular, it tells us that if we want to generate a convex cost function that satisfies the property on the previous slide, that it has this particular set of gradients, then all we need to do is define some appropriate conjugate function and set the domain of that function, this domain here, to be this hull, the set of gradients that we want to achieve in our function. Again, I'm totally hand-waving here, but I just want to give you the general flavor of the result that we can use to get these cost functions that satisfy our property. Okay. So this is nice. I'm claiming that all we need to do to find a cost function is set this domain to be what we want it to be and choose some strictly convex function r. But the next question that you might have at that point is, well, how do we choose this function r, right? There are a lot of different choices that we could come up with for this function r, and they will all lead to different markets. So how do we actually do that? And this is where we can actually borrow a lot of techniques from the online learning community. In particular, it turns out that there's a really nice connection between what we're doing and what's being done with the problem of online linear optimization. And in fact, this conjugate function that we're trying to come up with here, this R function, plays a really, really similar role to a regularizer in the online linear optimization community. And this is really nice because it allows us to borrow techniques from online linear optimization and this extremely well-studied literature of how to choose regularizers, and we can essentially, choose conjugate functions in a really similar way, and a lot of the same nice properties will carry over.
How does the regularizer look like? How does the regularizer look like?
The regularizer?
Yeah.
So I'm not going to go into too much detail on that. Usually it has some quadratic form or some entropy form. So
does it depend on the domain that you're using?
It does not depend on the domain, but it will depend on properties of the outcome space.
Okay.
They're not going to go into that too much. So I want to go into this connection a little bit more because I think that this is, first of all, really beautiful and also perhaps interesting to this audience. So I know that I've only got a few minutes left here, so I'll go through this a little bit quickly. But let me start by just giving some quick background on this particular problem from machine learning, this online linear optimization problem. So online linear optimization it's just basically a slight extension of the learning from expert advice setting, if people are familiar with learning from expert advice. The idea is that we assume that there's some set of experts, which are basically anything that you want to define them to be. These experts could be, real people who are giving you predictions. They could be other learning algorithms. They could be features, whatever you want them to be. And we're going to want to choose actions based on the advice of these experts. So if we imagine that our experts are people here, then the way the setting works is that we're going to proceed in a number of rounds. At every round, our algorithm is going to have to select some set of weights over these experts. In the basic learning from expert advice setting, these weights have to be a probability distribution. In the more generalized online linear optimization setting, this weight vector has to be chosen from some more general convex set. But the algorithm is going to select these weights. The experts are all then going to suffer some loss. So it's typically assumed that these losses are, in some bounded range, say between 0 and 1. They can be adversarially chosen. So an adversary who actually knows what your algorithm is doing here could select these losses, right? As for what these mean, well, if you're thinking about something like, classification using expert advice, then maybe these losses would be 1 if you've made a mistake and 0 otherwise, something like that. But it's a pretty general setting. These can be just set arbitrarily. And after this happens, our algorithm is going to suffer a loss, which is the dot product between the set of weights that the algorithm chose and the set of expert losses. So in the expert advice setting, if these weights are a distribution, then you can think about this as the expected loss that the algorithm would have suffered if he chose one of these experts to follow according to this distribution. So that's online linear optimization. In this setting, if you want to know what the goal is, well, ideally, we'd like to do something like bound the cumulative loss of our algorithm, so the cumulative, the sum of these dot products over time. But in general, we can't do that if we're thinking about this adversarial setting, because the adversary can just make all of these losses really high all of the time, and then there's nothing that an algorithm can do. So instead, this setting is usually analyzed in terms of regret. So the idea here is that we want to minimize not just this cumulative loss, but the difference between the loss of our algorithm and this term here, which is the loss of the best one of these, well, in this more general setting, it's the loss that we would have gotten if we had used the best possible set of weights in hindsight on every step so far. So this LT here is the cumulative loss vector of the expert, so it's just the sum over all time steps of the expert's losses. And again, this is the difference between our algorithm's loss and the loss of the best fixed weight vector in hindsight. And I know I'm going through this rather quickly. I'm happy to take questions on any of this after. But I just want to mention that in the setting, one particular class of algorithms that has been really commonly used and which you can get really nice guarantees for is what's called these follow the regularized leader algorithms. And the idea here is that the algorithm is going to choose its weights for the next time step to be the weights that minimize the sum of two different terms. So the first term is just the cumulative loss that we would have received by using those weights so far on all of the previous rounds. And the second term is a regularization term, which is basically added in there to add some type of stability. Because if we don't have this term, if we don't have this stability, then you can come up with examples where just minimizing past loss is really, really bad. We want some type of extra stability added in there. So that was a slight detour to this online linear optimization setting, which some of you may have seen before. And again, there's a huge literature here and a huge literature on choosing these regularizers. And again, not going into much detail at all, I just want to put up these two problems side by side. And if you kind of squint a little bit and ignore the, don't try to think too much about the details, but just kind of glance at these problems side by side, you can see that all of the math that's going on here is really pretty much identical. Right? So in the learning setting, we're choosing these weights over items. In the market setting, we're choosing these prices over contracts. In the learning setting, kind of our state so far can be measured in terms of this cumulative loss vector. In the market setting, our state so far is measured in terms of our vector that tells us how many of each contract has been purchased. We said that this follow the regularized leader algorithm selects weights using a function of this form. This looks really, really similar to this function that we want to use to select prices here. And the only thing that looks a little bit different is our goal. So in the learning setting, we're trying to minimize this regret. And in the market setting, well, there are lots of different things that you might try to minimize, but one thing that we care about a lot is the amount of money that the market maker can lose in the worst case, if the worst possible outcome happens for him. And we can actually write that as this quantity here, where on the right we've got the amount of money that the market maker has collected from all of the trades that have happened so far, and on the left we have the amount of money that the market maker has to pay out given these trades if the worst possible outcome for him happens. Right? Again, I know I'm going through this really, really fast and don't expect people to absorb all of the details. I just want to give you some sense that there is really a similarity going on here. And in these last two terms are where things look a little bit different, but actually these aren't that different. If you think about this term here, the amount of money the market maker has collected, and